Hi everyone. Welcome back. I hope you are refueled after lunch. I'm going to introduce our next talk. I'd like to introduce Ehsan, who is a scientist from QCRI. He specializes in multimodal language processing, and he has a PhD from the University of California. And also Sahra, who's actually from Google DeepMind. She's a research scientist, and she specializes in private inference and contextual integrity in LLMs.
Thank you so much for the introduction, and it's really nice to meet everyone. So I will be giving an introduction to deep learning. So I'll sometimes ask you how well you're familiar you are with all these concepts, and then I expect a lot of nods or like shaking heads, so I know if you're all still interested in the talk. So I'm a research scientist at DeepMind, where I work on like safety and privacy evaluations of language models. So the latest product that I was proud to be part of is Project Mariner. Project Mariner is a web UI agent that you can give a task to. So find the most famous post-impressionist colorful painting on Google Arts, and then order paint for me on Etsy. So you tell it to do that, and then it's like an agent that can access prompts, so it can type stuff, it can click on stuff, and do the things you want it to do. It basically is, it does some reasoning, and then I'll show you a quick demo of how it works. You can also just Google Project Mariner and you will watch it on YouTube yourself in case the technical difficulties won't allow you to look at it. But basically what it does, it has a language model as a backend, and then learns computer control and can move your mouse, and it will put, for instance, the paint into your Etsy card, and then put in all the information like your credit card number, etc., for you to be able to order the paint on the internet. And it just makes it considerably easier to automate a lot of tasks like filling out forms or doing trainings online.
We've been exploring what's possible in the domain of human-agent interaction. Today I'm going to walk you through a picture of art and starts looking at them to find a colorful option. The agent used its multimodal understanding capabilities to find a colorful painting of irises and clicks on it. After finding this painting, it navigates to Etsy by typing in the URL. It clicks on the search bar and searches for colorful paints. So now it's looking at different paint sets, and the agent gives us a sense of what it's optimizing for. As you can see, it's optimizing for price and visual appeal. The agent clicks on a set of watercolors that appears to be a good fit. It's then added to cart. After a moment, the agent asks me if it should proceed to checkout. This is an early research prototype, but it's a great experience.
So here you see what the model can do, and obviously it gets access to all your credit card, like if you can give it access to a lot of information like credit card information, home address, for it to actually be able to finish like the purchase. And I work on like evaluating its safety and like privacy, making sure that it knows when it should not just pay suddenly 10K with your credit card information, and instead confirm with the user what it's doing. So that's pretty cool, and that's where deep learning is right now. But where did it actually start? It started like, AI started in the 1960s. Deep learning is a subfield of AI that only emerged like 1986 after we got something that's called vector propagation, and I'll talk about that later as well. But before that, AI was mainly rule-based models like robots that knew exactly how chess works. They didn't learn anything from data. Deep learning is the part that uses neural networks, like deep neural networks that are trained on data to achieve more complicated tasks. So I guess in traditional statistics, we started off with regression, so we have like an original representation, and that's mapped with weights to like a classifier. And deep learning now adds one thing, namely this like hidden representation, where it maps the original representation to the like a hidden state, and this is how you can do classifications. So just like to summarize it, you get some numbers in, you multiply them with weight, and then you get the hidden representation. And now the most important part of this is that there is an activation function which is non-linear. This activation function, if it didn't exist, this whole model would just collapse to linear regression, which is something we don't want. We want like a really complex model, and like this activation, which is here is sigmoid, makes that possible. So the sigmoid is just a function that maps any kind of number to a range between 0 and 1. So you can use it, for instance, also for like probabilities in the end. So here, for instance, when we do the classification, we get a number in the end, and we want it to be a probability because it's a probabilistic classifier, and then we use the sigmoid again. So who of you knows what an activation function is? Raise hands. Oh, that's a lot of people. Okay, what's your favorite activation function? Someone shout.
ReLU.
ReLU, okay, that's amazing. I'll tell you why ReLU is the best activation function. So the sigmoid is great because it goes between 0 and 1, it has a smooth gradient, that's amazing. But the problem with the sigmoid is that it maps everything to positive range. So our output will always be positive, and that makes learning neural networks really hard because if you want to go into one direction, all the weights, all the gradients will look into the same direction because after the first hidden layer, everything will be positive, and that's really annoying. How can we solve that? We use the hyperbolic tangential function, which will map everything to -1 to 1. So we solve the problem of being positive all the time. But the problem of both of these functions are that they have vanishing gradients for like really large and really small numbers. Vanishing gradients are bad because that means if you have really large numbers and you get their gradients, they're basically 0, so your model is not learning anything. So you can try to train a neural network, but with really large numbers, nothing will happen. And that is where the ReLU comes. So your favorite activation function is basically just linear for positive numbers. And because of that, like it doesn't have any gradients, like any vanishing gradients for the positive side. But what happens on the as a like drawback is that everything that's smaller than 0 is just negative. It's just 0. And here you have basically the problem, the dying neuron problem of the ReLU. Is that you will have some neurons which will just always be 0, and you can try training your neural networks, but they will always stay 0 and nothing will happen. So how do we solve that? We get the leaky ReLU, and then the leaky ReLU is the same as the ReLU, but just for negative numbers, you have another linear function, so you still have a gradient there, and then something second there, so that's great. But now you see like it has this really ugly thing in the middle where it's not smooth. So here, you see there's not a smooth gradient. So what smart mathematicians did, they came up with like other functions like ALU, CALU, that all do something similar like leaky ReLU, but they basically just interpolate between the linear function of the ReLU to something that is smooth and not 0 on the negative side. Okay, so we now know what an activation function is, and we can do a forward pass to neural networks. That's the first thing we did. So what do we do then? Then once we did that, we can compute the loss. So this is the empirical risk. So what we do when we compute the loss is empirical risk minimization. So we compute the empirical risk, which is just like the loss between a true value and the predicted neural network output. And an example of such a loss function is just like subtracting the true value minus the predicted value, and then you can analyze any deviation. And now once we did that, what we want to do is we want to learn to go towards the direction of the steepest descent. So we compute the gradient, and the gradient tells us where this direction is. And that's basically just the derivation of the loss function to each of the parameters of the neural network. So here, for instance, you see a figure where you can, where we want to be is here. And in order to get there, when we start at the top here, we just want to find each gradient at each point and then slowly go towards the minimum. And we do that by like taking the parameters. The parameters are here called theta. And then for at each time point, we subtract alpha times the gradient. And alpha is called the learning rate or the step size. Okay, so we know how to do gradient descent. And you do that by taking all your observations, computing your loss on all observations, and then going down. So now, as you see, we start with some set of parameters, and then we compute the gradient. That means when we have a neural network, we have to initialize the weights somehow. So we cannot train the neural network from scratch, we have to set the weights to something. And like a really easy solution would be to set all the weights to 0, so you start a neural network and then everything is just 0, like in the beginning. So in the beginning you could have set everything to 0, but instead what we will do is we use weight initializers that sample from random distribution. The reason for that is if we set all the weights, all the parameters of the neural network to 0 in the beginning and then try gradient descent, all the gradients will be 0. Or like when we set all the parameters, for instance, to 1 and then we do gradient descent, all the parameters will have the same gradient, like nothing will be learned. So what is important is that all weights are different, and that's what we use now, what we use random functions for. So the Sahra weight initialization samples from a uniform or Gaussian distribution that has a variance of 1 over n. And this variance is motivated by showing what actually happens when you compute like a hidden representation. So this is just one of the neurons within the neural network that gets like inputs from n different features. So the variance of this thing will be the variance of the features times the variance of the weights. So if there are n nodes right before this one, then the variance of this thing will be n times the variance of the features before. So if you want all the nodes in your neural network to have similar variance, what do? You just divide by n, like experiment by n, and then you make sure that the variance will be the same for all your nodes in your neural network. And that is important because this is how we make sure that there is not one part of the neural network that learns everything, but we want every node to have this similar chance to learn something. Okay, so this is only true when we do the forward pass. So when we do the forward pass, so we go from left to right in the neural network, that is where we have n inputs. But now what happens when we do the backward pass? So when we do the backward pass, we take the output of the neural network and go back. So we go from the other side to the back side. So we also have to see how many nodes does A go into. And this is why there is another weight initialization, normalized Sahra weight initialization, where you not only divide by n, but also plus m, and it is the number of the outputs from the layer. And this is so you can make sure that when you go to the other direction of the forward pass, that backward pass, you still kind of normalize the variance of all the nodes. Okay, but what was your favorite activation function again? Amazing. Okay, cool. So basically, the problem there is before we assumed when we have the ReLU, what happens is you have half of your outputs will be 0, right? So half of the nodes don't have any input, which is why Sahra weight and normalized Sahra weights don't work. And this is why for when you use ReLU, you actually multiply your weights by 2 because you want to basically make up for the half chance that they might just be 0. So that is the motivation why when you have edu or relu or whatsoever, you actually want he weight initialization or not the Xavier initialization. Okay, cool. So I already spoiled you what the backward pass is, but now we will explain it a bit more in detail. So now we have the loss and we want to learn our parameters. And that is what happens in learning, is we have to compute the gradient. And how do we do that? So now imagine we want to compute the gradient of this parameter here. And in order to do that, we can just use simple chain rule and compute the loss towards f out. So that is the thing after the activation function. Then we compute the gradient of f out to f in. So that is the activation function derivative, like for instance from the sigmoid or UL, and then from f in to u1. And so this composition gives you the gradient of u1. So it's really simple, just like chain rule. You can set the numbers, and then you see, okay, your gradient is minus 0.01. And you can update your new u by just having your old u and subtracting your learning rate times your gradient. And now imagine you want to go further back, so you go from the right side of your neural network to the front, and want to compute the gradient of w. What do? You just go again, step by step, compute the gradient through each step. And we already know the first two gradients, right? We already know the gradient to f out and from f out to f in. And this is what we save. So basically the entire, like how Jeffrey Hinton, one of the reasons he became famous, he has a lot of reasons why he's famous, but one of the reasons he became really famous is because he said, oh, when we go, instead of like computing the derivative from going left to right, we go from right to left, and then we just save the gradients we already have, and we use them. And that's why gradient descent, when you have a computational graph, and like pi towards TensorFlow, can be really efficient. Okay, so now we summarize gradient descent. What do? We first initialize our weights. Then for a fixed number of epochs, so we can just say, okay, I'm computing budget at 1 day, just like for 10 epochs, do the same. Or when our validation loss is not increasing, so you can just have like you can track the accuracy on a validation set, and then just check that this validation set loss does not go up too much every time you train. You first do a forward pass, so you go from left to the right of your neural network, you compute your loss, how bad is your neural network doing, then you do the backward pass, computing all the gradients, and then you update your parameters. And so this is gradient descent, which is really memory intensive because it assumes you do that with your entire data set. Sometimes your entire data set doesn't fit and it's just taking really long. For instance, for like neural net, like for natural language processing, the data sets are huge. So what you can do instead is just do this per observation. That's called stochastic gradient descent. But as you see here, stochastic gradient descent has the disadvantage that it's really noisy, because if you just do it by one observation at a time, you introduce too much noise, and it's also taking really long if you want to get through the entire corpus of your training data. Instead, what you can do is mini batch gradient descent, where you assume, okay, I'll just do it for 200 examples at a time. So 200 examples, you just sample from a training data set, or like 2,000 examples, and you just over them average your gradients and do a step. Then there's SGD with momentum, which is like SGD, but it's like you save your gradient. So your gradient here is called like eta O. You save it, and then you just update your new gradient. Is not just the gradient, but like the old gradient minus the. So you have like a memory of the gradient. This is what's called momentum. So if you had a really big gradient before, now it's really small. Your update is still like a medium average update. So that is also amazing. But then what you can also look at, instead of just looking at your old gradients, what you can look at is the squared old gradients, like the Hessian matrix. And why you would want to do that is because it will give you adaptive learning rates. So each parameter in ADAPT, each parameter in the neural network has its own learning rate. So if a parameter was updated a lot and it's revised by the Hessian, you make sure that that parameter doesn't get updated too much in the next steps, or something doesn't get updated at all. If you divide by the squared gradient, you make sure that in the next step it will get more updates. So this is how it can treat, like it can work well with like sparse data. And the problem here is that because you divide by this cache, so this cache is the squared order gradients, you have the problem that the further along you are, the more gradients you accumulated, and then at some point you will not be able to learn anything anymore. So this learning rate will just become zero. And what RMS prop does, this RMS prop is an algorithm that was, by the way, never published. It was just Jeffrey Hinton being a genius again, and like in a presentation, just like giving a lecture, being like, oh, this could maybe work, and then he just wrote it out, and then this optimizes suddenly work. So he said, instead of just saving the, just adding up the old squared gradients, we do like exponential moving average, and then you basically decrease how much everything changes. So this is the gamma times cache old plus 1 minus gamma with the new one, instead of just adding everything up without the gamma term, which is what ADAPT does. And now if you combine these two approaches, RMS prop and SGD with momentum, you get Adam, and Adam is still probably most used optimizer nowadays. So yeah, this was just a really quick intro, so like people who didn't read with neural network training before know what it is. And like now that we did that, we can train neural networks, and I want to like maybe present one area of them as convolution in neural networks. So assume you want to train an image classifier. How images are represented is on the left you see the image, on the right you see its pixel representation. So in black and white you get numbers from 0 to 255 for each pixel telling you how black it is. And if you now have colorful images, you would have a 3D matrix of that, where for each color, yellow, red, and blue, you would tell at each pixel what is the combination of all these colors. And now, one of the things like someone found out like a couple of decades ago is the Sobel filter. That is when you, so if you multiply these pixels by a matrix, you can actually do edge detection. So you can just see this matrix like this +1, 2, +1, this is the Sobel filter. And if you convolute that with an image, it will tell you where the edges are. And how it does this is it can like, this is a product, like the matrix is a product of two vectors. The first vector, 1, 2, 1, gives you an average over all the pixels. So it's basically like pixel before, the pixel you're at, and the pixel after. And then 1 minus 1 is a differentiation kernel, so it tells you I'm looking at the left side of my kernel and I want to subtract the right side, and this is how you get basically the contrast between what is happening to the left versus what is happening to the right side of a pixel. And then what convolution now means is that you take that matrix and you multiply it element-wise with each pixel. So here you see for like that part in the top, the 0, 255, 255, you just subtract each number in the matrix with each number in the pixel, and you get like, this is how you get the weird picture of Albert Einstein. Okay, so the Sobel filter is a convolution that is not learned, but like just like was like, oh, this was really cool, like I can just work it out and like this actually work. And now what we want to do in deep learning is we want to learn these convolutional kernels with data. So for instance here our input is 3 times 3 and we have filters that are 2 times 2. We can like multiply this on each of the sides, so upper left corner, upper right corner, and this is how you can like basically get a hidden representation for our input. And the benefit of this is that now our weights don't need to be as big as our input. So if we have an image that's, for instance, 1024 times 1024 times 3 because it's like colorful. These are a lot of parameters if we just did it with like normal weights, right? Like times weight. But like if we could apply like a 2 times 2 filter to it, which would have only four parameters instead of 1 million. And it also allows for, so this is how you save a lot of memory. And then what you can also do is, because if you do that, as you might have noticed earlier, the output becomes smaller so you see if you continue this, you will get the 2 times 2 output. And in order to make sure that your output doesn't get smaller than before, you can do something that's called padding. So you just add zeros to the edges of the images, and then you make sure if you apply the filter, the output thing will be as big as the input. So does everyone like kind of get what the convolution is? Yes, amazing. Thank you so much. Great audience. I love it. So yeah, another thing aside from padding that you can do is like strides. So instead of going like just moving your convolution funnel one pixel at a time, you can also move it 2 pixels. Like here, this is like of stride 2, or like even more, and then you just save even more parameters. So you can like half the size of your output. There's something called max pooling. So instead of just multiplying a matrix, we just take the maximum of the input. So here, for instance, a max pooling with 2 times 2 would go here, and then you see at the top right corner, at the top left corner, the maximum is 8, the top right corner would be 6, and the top lower left corner would be 9, etc. There's average pooling, where you also again do the same with your filter, but now you just take the average. So here you take the average of 1, 1, 2, 3, it's like 1.75 in the lower right corner, and so on. And then there's also another block, so these are just like blocks you can add to your neural networks to make them cooler. It's called the residual block. And what the residual block is, because like the problem with neural networks is the larger they get, you'll suffer from vanishing gradients, because the gradient in the beginning of your neural network, at the back of your neural network will have forgotten what the input was, because like it has like you have the forward pass was just too long. So what you do is you add residual connections where you add your input again and again, and this is how you can make really, really long neural networks that won't suffer from vanishing gradient. And that was something Microsoft introduced. And yeah, so here you see a couple of famous CNN architectures. They just use everything I just taught you, so you could come up with the next amazing neural network architecture that's won amazing prizes by just like combining convolutions, average pooling, max pooling, residual connections. Here, this is a unit. The unit has been proposed for image segmentation, and is nowadays one of the main building blocks of diffusion models. So any image generator that generates images for you from ChatGPT, etc., uses probably something like a unit. And how these things work is they use convolutions, so they can sometimes crop images and make them smaller. And then they use the residual connections, which are here in the middle. So the gray arrows are the residual connections. Oh, this is horrible. Or they use max pooling, and so basically all the like small building blocks you just learned, you can like apply in different ways to like do really cool things. So these are the things you would use for methods like for image generation or image segmentation, anything with images. But when it comes to text, you have the difference that now you have something that goes from left to right, so you cannot really apply like the convolution anymore because you have like a one-dimensional setting. So what you do instead is you use recurrent neural networks. So recurrent neural networks work as before. So you like take input. So for instance, this is a word, and you use a tokenizer to like find the find a digit, like a numerical representation of that word. So here it's just one hot encoded, you have a dictionary of all the words that's possible, and then this is just the first entry, so it like gets a 1 there. And then with the multiplication of the weight matrix, you get the written representation 0 as Z. And then you go to the next word, so this is, so it's the second word in the dictionary. You take the hidden representation of your word before, multiply it by V, and then add it to the hidden representation of your second word, and so on. So you can do that, etc., etc. But does anyone know what the problem could be with this? If you keep doing that?
Vanishing gradients.
Yes, amazing, amazing. So many vanishing gradients. Okay, so really sad, so we keep having this problem. So what we do instead is we do long short-term memory. And how this approach works is that you want to make sure that you don't have vanishing gradients and you remember your previous states. So you do that by introducing something that's called a cell state, S. And what the cell state does is it basically, you tell it to remember everything you did before. Okay, so the cell state is the memory, and you have a forget gate, so it like works by having different gates, and forget gate and output gate. So here the forget gate E tells you what you want to forget from your state before to the next state. And the forget gate is just a function of your word, like X, so this is good news. And then Z is just the hidden representation of your recurrent neural network, right? And then this gets inputted into the forget gate, and it tells you what should you remember in the next state. And then the input gate tells you what of your current word should go into your new cell state ST. So that is the new cell state S. It's like a combination of the old cell state ST-1 and your new word XT and the old representation, the representation of the old word Z. And then you also get an output gate, and the output gate tells you what from the current word will get into the output of the new network, which is the ZT. The ZT. So basically that is, if you look at it, it's basically just a recurrent neural network, but in the middle it has all this like, the cell state that remembers, forgets, inputs from the current gate, and then the output gate gets you, combines the cell state S and your current word and the old representation into the new representation. So as you see, this is like really like kind of artificial, like it just tells you, okay, we do this and we do that, and it's a bit complex, like there are a lot of operations, and the problem is now like we're having more and more data. So if you see here, you can see how much data is like transmitted through global internet traffic, and that's also ultimately the data that probably most companies want to train on. It's like in 92, it was like 100 gigabytes per day, and now we're like at 150,000 gigabytes per second. So we have way more and more data. So this LSTM architecture cannot, it's too complex to learn with so much data. And also, maybe instead of trying something artificial, we can like have something that just learns how we go from one, what we should remember, instead of like artificially making out an input gate and a forget gate. And that's where transformers come in. So I'm introducing Essa, who will give the next talk on transformers.